Hello everyone, I'm Hoi-Gi from Seoul National University. Today, I'd like to present our work titled Efficient Personalization of Quantized Diffusion Model Without Backpropagation. Personalization in text-to-image diffusion models lets the model generate images of a specific subject or style using just a few reference images. For example, with a few photos of a corgi, the model can create new images of that same corgi like at the Acropolis or getting a haircut based on text prompts. Despite its benefits, personalization poses challenges. It usually requires training which consumes large memory for activations, optimizer states, and etc. This makes it hard to run on edge devices where personalization is most needed due to privacy concerns. Quantization is often used for edge deployment. It reduces memory by converting float weights and activations into low-precision formats like integers. But quantization includes rounding, which is non-differentiable, making backpropagation unusable. To solve this, we propose ZOODiP, a personalizing method using zeroth-order optimization which avoids backpropagation. Our methods build on texture inversion, and by leveraging zeroth-order optimization, we are able to fine-tune stable diffusion with less than 2.4 gigabytes of VRAM. Despite the significant reduction in memory usage, our method achieves comparable performance to existing personalization approaches based on backpropagation. This figure shows the ZOODiP pipeline. Like texture inversion, we train a token embedding to represent the subject or style. We add noise to reference images and train the model to denoise it using the text token as condition. Let's focus on zeroth-order optimization with Subspace Gradient or ZO with SG. Zeroth-order optimization or ZO estimates gradients by adding random perturbation to parameters and observing loss changes via forward passes. It has been used to optimize non-differentiable objective like accuracy, but to our knowledge, it hasn't been applied to quantized models. Although ZO reduces memory, its gradient estimates are noisy. To mitigate this, we first run textual inversion, then apply PCA on the embeddings, keeping only the top k eigenvectors. At inference, unused components remained at their initial values. Surprisingly, just 256 dimensions, which is one-third of the original 768, still enable effective personalization. This suggests that only a subset of dimensions is actually effective for personalization. Based on this insight, we propose a subspace gradient approach that reduces the noise in the estimated gradients by constraining updates to this more meaningful subspace. We began by initializing gradient buffer of length tau. For tau iterations, we store the estimated gradients in this buffer. Then we perform PCA on the collected gradients to identify directions with high and low variance. We construct a projection matrix P nu using the eigenvectors whose cumulative variance is less than 1 minus nu. For the next tau iterations, we project each estimated gradient onto P nu and then remove the projected components, effectively filtering out the low variance directions. After every tau iterations, we repeat the subspace generation process. This subspace-based filtering is applied throughout the entire optimization process. Next, I'd like to introduce our second key technique, Partial Uniform Timestep Sampling or PUTS. In conventional personalization training, diffusion time steps are sampled uniformly across the entire range. However, our experiments revealed that only a subset of time steps, particularly those closer to the noisy end, are actually meaningful for personalization. Based on this observation, we propose partial uniform timestep sampling, which samples timesteps uniformly from a restricted range, focusing on the most effective regions for training. To evaluate the personalization performance of ZOODiP, we conducted quantitative comparisons with several existing fine-tuning methods for quantized models, including QLoRa, Pekka, TuneQDM, and gradient-free texture inversion. The results show that ZOODiP achieves comparable performance in both image and text alignment. while maintaining the lowest memory consumption among all methods. Additionally, since ZOODiP performs personalization using only forward passes, it demonstrates the fastest training speed among all compared methods. The qualitative results show that ZOODiP is able to faithfully reproduce the reference subject while also accurately following the given input prompt in the generated images. We also observed that ZOODiP can successfully perform style-based personalization, not just subject-specific generation. We conducted evaluation studies to evaluate the individual components of SG inputs. Each component showed a positive impact on performance. Additionally, an extensive hyperparameter study on tau and nu showed that ZOODiP is robust to hyperparameter selection. We also compared various timestep sampling strategies and found that puts consistently outperformed other approaches, further demonstrating its effectiveness. Finally, experiments with different combinations of TU and TL support both the validity of puts design. Thank you for watching our presentation. For the code implementation, the full paper, and additional results, please visit our project page via URL or the QR code shown on the slide. Thank you.